Hello friends, it is our second lecture over the ionic equilibria, and in this second lecture we will look about the common ion effect and solubility product. Before talking about the common ion effect and the solubility product, it is very important to understand the electrolyte. So for this, we had seen the Arrhenius theory of the dissociation. According to the Arrhenius theory, any substance undergoes dissociation in water to produce the ions, positive ion and the negative ion. That substance is known as the electrolyte. Electrolyte are of two types, strong electrolyte and the weak electrolyte. And we had seen the difference between strong electrolyte and the weak electrolyte. Strong electrolyte dissociates completely to produce the ions. Weak electrolyte dissociate partially. Strong electrolyte having high value of degree of dissociation. Weak electrolyte is having low value of the degree of dissociation. Strong electrolyte produces large number of ions in water, so it is good conductor of electricity in solution state, while the weak electrolyte is poor conductor of electricity in solution state. Example of the strong electrolyte is sodium chloride, hydrochloric acid, potassium hydroxide, while the examples of weak electrolyte is acetic acid, ammonium hydroxide. So with this knowledge of the electrolyte, strong electrolyte and the weak electrolyte, we will understand the common ion effect. So for common ion effect, this question, understanding and the answering of this question is very important. What will happen when strong electrolyte is added to a solution containing the weak electrolyte having the common ion? And according to the common ion effect, answer is the dissociation or the degree of dissociation of weak electrolyte decreases. So common ion effect term is related with the strong electrolyte, weak electrolyte and the common ion. So this is the equation for weak electrolyte. A weak electrolyte AB undergoes dissociation in water as A plus ion and B minus ion. And to this solution of weak electrolyte, we are adding the strong electrolyte AC. So it undergoes dissociation as A plus ion and the C minus ion. So in that, the A plus ion is common, concentration of A plus ion increases. So to control the concentration of A plus ion, the dissociation of the weak electrolyte proceeds in backward direction, means its degree of dissociation decreases. This is common ion effect. So we are defining the common ion effect as the phenomenon of decreasing the degree of dissociation of weak electrolyte due to addition of strong electrolyte having common ion. So this phenomena is related with the controlling the concentration of common ion arising from the weak electrolyte and the strong electrolyte. As a result, only way to decrease the concentration or the degree of dissociation of weak electrolyte. We will look the examples of common ion effect. First is the dissociation of acetic acid in presence of sodium acetate. So the acetic acid is a weak electrolyte. It undergoes dissociation in water as acetate anion and the H plus ion. Sodium acetate is a strong electrolyte. In water, it undergoes dissociation as the acetate anion and the sodium ion. So in that dissociation, the concentration of acetate ion increases. It is a common ion. So to control the concentration of the common ion acetate, according to the Lee-Chatriel principles, the equilibrium of weak electrolyte shifted on the backward direction, so decreases the dissociation of weak electrolyte, that is the acetic acid. So to control the concentration of common ion, the degree of dissociation of weak electrolyte, acetic acid decreases. So both the acetic acid and the sodium acetate, this mixture acting as the acidic buffer in the solution, it is used for the controlling the pH of the solution on acidic side. Next example is the dissociation of ammonium hydroxide in presence of the ammonium chloride. So ammonium hydroxide is a weak electrolyte. In water, it undergoes dissociation as ammonium ion and the hydroxide anion. Ammonium chloride is a strong electrolyte. In water, it undergoes ionization as ammonium ion and the chlorine ion. So, because of addition of the ammonium chloride in the ammonium hydroxide solution, the concentration of the ammonium ion increases. It is a common ion. So to control the concentration of ammonium ion in solution, according to the Le-Chattel principle, the equilibrium of weak electrolyte ammonium hydroxide is shifted on backward direction, so decreasing the dissociation of weak electrolyte to maintain the concentration of ammonium ion. So in this case, the ammonium ion is a common ion, and to control the concentration of ammonium ion, the equilibrium shifted on the backward direction. So as a result, the concentration of ammonium ion decreases. So along with the ammonium ion, the concentration of hydroxyl anion also decreases. So it is also used for the controlling the pH of solution of alkaline site. The mixture of ammonium hydroxide and the ammonium chloride used as the alkaline buffer in the solution. So common ion effect is very useful for controlling the pH of solution in the form of buffer mixture. Now we will look towards the uh, now we will see the solubility product, that is KSP. So in order to understand the KSP, we have to understand the sparingly soluble salt. The solubility product, this concept is applicable to the dissociation of sparingly soluble salt, and it is a parameter used for the measurement of dissociation of sparingly soluble salt. So we will look what is sparingly soluble salt. Salt that dissolves only a very limited extent in given solution at given temperature is known as the sparingly soluble salt. Example is calcium sulfate, silver chloride, barium sulfate, and the lead chromate. So these salts or these solids are practically insoluble in the aqueous solution, and very little extent of the ions are produced in solution, means their dissociation is very weak. So this is example of silver chloride. This is very common known sparingly soluble salt. So this is a flask in which we are taking the water, and in that water we are adding the silver chloride sparingly soluble salt. So after addition of silver chloride sparingly soluble salt in the water, its very little fraction of the Ag plus ion and the Cl minus ion undergoes the dissociation, means its dissociation is very weak. And this dissociated part remains in equilibrium with the solid. So silver chloride undergoes dissociation as Ag plus and the Cl minus ion, and it is represented by this chemical equation. Silver chloride solid sparingly soluble salt undergo dissociation in aqueous solution as Ag plus ion and the Cl minus ion to a very limited extent. Now we will derive an equation for solubility product for the KSP. So consider the sparingly soluble salt AXBY undergoes dissociation to a very limited extent to form A plus Y and B minus X ion in water. This is represented by this chemical equation where X and Y are the stoichiometric coefficient of the equation. The solid AXBY undergoes dissociation in aqueous solution as XA plus YB minus X ions. So according to the law of mass action, at equilibrium, the rate of reaction is directly proportional to the concentration of reactant. So in forward direction, the reactant is AXBY, while in backward direction, the reactants are these ions. So according to this, the equilibrium constant K is equal to the concentration of A plus Y ion into concentration of B minus X ion divided by concentration of solid AXBY. But the sparingly soluble salt undergoes dissociation to a very limited extent. It means that it is practically insoluble. So we are rearranging this equation as equilibrium constant into concentration of AXBY is equal to concentration of A plus Y ion into concentration of B minus X ion. X and Y are the power of the stoichiometric coefficient according to the equation. The sparingly soluble salt is practically insoluble in water, and it undergoes dissociation to a very limited extent. It means that the concentration of AXBY remains the constant or unchanged even after dissociation. So we can say the one constant into another constant is a constant. So K into concentration of AXBY is equal to constant, and that constant is the KSP, that is solubility product. So finally equation becomes KSP is equal to product of ionic concentration of A plus Y and the B minus XY raised to the proper power according to the stoichiometric coefficient. Means X and Y are the power of the concentration according to the stoichiometric coefficient in the equation X minus Y. So here we understood what is solubility product. The solubility product is the product of ionic concentrations raised to the proper power according to the stoichiometric coefficient. So this is the multiplication or the product of the ionic concentration, that is known as the solubility product, and this solubility product is constant at constant temperature. So we can define the solubility product as, in a saturated solution of sparingly soluble salt, the product of ionic concentration when raised to the proper power according to the stoichiometric coefficient of equation is constant at constant temperature, and this constant is known as the solubility product. In short, the solubility product is the product of ionic concentration of the ions for sparingly soluble salt. So according to that equation, the solubility product is the product or the multiplication of the concentration of the ions. So there are different types of the sparingly soluble salt. The sparingly soluble salts are listed in this table with their formula, with their dissociation equation and the equation of the solubility product. The first is silver chloride, where X and Y is equal to 1. Silver chloride undergoes dissociation as Ag plus ion and the Cl minus ion. So Ksp is equal to product of concentration of Ag plus ion and the Cl minus ion. Second is the barium sulfate. Here also X and Y is equal to 1. Barium sulfate solid in aqueous solution undergoes dissociation as 1 barium ion and the 1 sulfate ion. So according to that, Ksp is equal to concentration of barium, the Ksp is equal to product of concentration of barium ion and the sulfate ion. Calcium chloride undergoes dissociation as 1 calcium ion and 2 fluorine ion. So according to that, for calcium chloride, the Ksp equation is the product of concentration of the calcium ion and second power of the fluoride ion. For lead iodide, it is same like calcium chloride. For the ferric carbonate, it is same like AgCl and the barium sulfate. For magnesium hydroxide, it is same like for the calcium chloride and the lead iodide. AgBr is similar to the AgCl. The dissociation of zinc sulfide is similar to silver chloride. Zinc sulfide undergoes dissociation to a limited extent as zinc ion and the sulfide anion. So Ksp is the product of ionic concentration of zinc and the sulfide. Copper hydroxide is similar to the calcium chloride and the lead iodide. And last is the strontium phosphate. Strontium phosphate undergoes dissociation to form three ions of strontium and the two ions of phosphate. So according to that, the Ksp is product of third power of strontium ion and the second power of the phosphate ion.